I'd like to have some sort of preliminary discussions around continuous time sort of linear state equations, and just to kind of talk through a couple key sort of initial concepts of this. One is, again, this is sort of your classical formulation, right? Where now you're going to be talking about I have x of t, which is my state variables. So this is a vector. It's a vector of state variables that I'm looking at here. I have my matrix A, which of course could be a whole set of time variable, whole set of elements. They could be a factor of time. And then I also have a whole set of inputs, and there's a matrix going into it as well. And then eventually I'm going to have an output, which is y of t, which will have parts of the states. Sometimes they'll be the states themselves. Certainly you could imagine C could be an identity matrix or some form thereof. But it could also be something that varies even over time. And then you have something also having the inputs and varying over time. The varying over time could be explicit signals, and so you could imagine like a demodulation or something like that. But typically when you're usually using these variables, you're usually assuming that there's some change in time because this linear system really came from a nonlinear system. And so, oh yeah, things might have moved on me, or time would have shifted it on me. And so that's really what you're often looking at here, but it could be any of these cases. Now, if I'm talking about multiple input, multiple output case, this would be exactly what the formulation I'd be talking about. Multiple input, its inputs are vectored, the outputs are vectored. Now we'll talk about a time invariant form. This is linear time invariant, and to get linear time invariance, it basically means that all of these matrices are constant. And in that case, it guarantees it's linear time invariant. There may be additional cases, but this certainly gives it to you without question. Now you could take this case, or you can take this case up here, and there's a special case of talking about a single input, single output case. This is actually very, very common in a number of cases. So now u of t is just a scalar, y of t is just a scalar. A is still a matrix, and because I now still have a vector of states. And this is a way to talk about what happens in multiple states, and then obviously a vector to kind of transform this back. This is this is one way of talking about I have a system with many, many states in it. So if I say I have an 8th order system, that means that x needs to be of length 8, even if I have a single input. So if I have an 8th order filter, that's how I would think about representing it. And so what I would imagine though is that what I'm basically going to get from u of t to y of t is a rational polynomial function, and a single one in the end, with all of these pieces and parts pulled together. But what you'll notice is that this dynamic for a, basically x of t dt, a x of t is still the primary dynamics that we look at. And so we'll often ask questions of how do we begin to transform this. And one neat thing that happens is that I can talk about, let's say I have a linear time invariant system, and I decide to transform this using, say, I want to transform my states x to x1 through a matrix T. Well, if I make the transformation and I transform A into A bar through T inverse, again, if you are thinking eigenvalue solutions, you're like, this feels very similar in terms of decomposition, and there's some really interesting values there. Shift B and C accordingly, I'm going to get this set of differential equation, but what happens is that I have the same, for a given input, I get the same output. But I've simply just shifted where my states are. These are considered two algebraically equivalent systems. You're like, okay, that's cool. But what's really neat is that then allows me to then say, all right, given I have a particular formulation, could I do something and shift that matrix in a way that's actually valuable for my analysis? Maybe it's an eigenvalue solution. Maybe it's something similar to that. But allows me to sort of shift and project my state variables in different directions to allow for maybe a better solution, maybe a better interpretation of what I want to look for.